A human sits cross-legged on a bare wooden floor, staring at a blank plaster wall. Outside, the sun has set, leaving only the dim, featureless gray of twilight to fill the room. The human does not move. Their breathing is slow, almost imperceptible. To an outside observer, they might appear to be asleep with their eyes open, or perhaps frozen in a moment of profound distress. In truth, they are engaged in one of the most quiet, involuntary struggles of the human nervous system. They are trying to make the world stand still. After several minutes of this intense focus, something unusual begins to happen. The flat, white surface of the wall, once solid and dependable, seems to shift. A tiny speck of paint, or perhaps a faint pencil mark left by a builder, begins to drift. It slides slowly to the left, then jerks back. If the room is plunged into total darkness, save for a single indicator light on an air conditioner, the effect becomes even more pronounced. The tiny green light begins to dance. It glides across the dark room like an insect, tracing invisible patterns in the air. The human blinks, and the light snaps back to its original position, only to begin its slow, ghostly journey once more. This is not a haunting. It is not a symptom of madness, nor is it a trick played by the light itself. The light is perfectly stationary. The wall is as rigid as the foundation of the house. The movement is entirely a creation of the human's own sensory apparatus. It is a phenomenon known as the autokinetic effect, a visual illusion that reveals the restless, anxious nature of the human eye. For centuries, this phenomenon baffled observers. In the late 18th century, the German polymath Alexander von Humboldt stood on a dark peak in Tenerife, looking up at the night sky. He noticed that the stars seemed to wander, drifting slowly across the blackness before leaping back to their places. He called this phenomenon Sternschwenken, or star swinging. Humboldt, a rigorous scientist, assumed he was witnessing a physical movement of the atmosphere, a cosmic dance occurring millions of miles away. It would take decades of research to realize that the stars were perfectly still, and that the grand cosmic movement was happening entirely within the fluid-filled chambers of Humboldt's own eyes. To understand why the wall appears to move, we must first look at the eyes themselves. A human often thinks of their eyes as cameras, capturing a steady, continuous stream of the world. But a camera is a passive device. It sits on a tripod, holding its frame perfectly still. The human eye is incapable of such stillness. It is suspended in an orbit of 6 highly active muscles, which are constantly twitching, pulling, and adjusting. Even when a human believes they are staring fixedly at a single point, their eyes are performing thousands of microscopic movements every minute. These movements are called micro-saccades. They are tiny, involuntary jumps, so small that the human is entirely unaware of them. They are accompanied by even smaller movements, slow drifts, and a constant, high-frequency tremor. The eye is, in essence, a vibrating machine. It never stops shaking. This constant vibration is not a defect. It is an absolute biological necessity. The photoreceptors at the back of the human eye, the rods and cones that detect light and color, are sensitive to change. If an image remains perfectly stationary on the retina, these receptors quickly become fatigued. They adjust to the constant level of light and stop sending signals to the brain. In laboratory settings, researchers have demonstrated this by using contact lenses equipped with tiny mirrors to project an image onto the retina in perfect synchronization with the eye's micro-movements. No matter how the eye twitches, the image remains perfectly static on the photoreceptors. Within seconds, the test subjects report that the image simply vanishes into a blank gray void. This is known as Troxler's fading. The micro-saccade is the human's defense against visual blindness. By constantly shifting the eye, even by a fraction of a millimeter, the human ensures that different photoreceptors are constantly being stimulated. The nervous system must keep moving to keep seeing. Within the center of the human retina lies a tiny, highly specialized depression called the fovea centralis. This is the region of sharpest vision, packed densely with millions of cone photoreceptors. It is the fovea that the human uses to read, to examine fine details, and to focus on the point of interest. However, this high concentration of receptors comes with a high metabolic cost and a rapid rate of adaptation. When the fovea is kept completely still, its signals decay almost immediately. The eye must perform micro-saccades not just to refresh the image, but to prevent the visual cortex from actively ignoring the input. But this creates a secondary problem. If the eye is constantly shaking, why does the world not appear to shake? When a human walks down a street, their head bobs, their eyes jitter, and their gaze darts from side to side. Yet, their perception of the street remains remarkably stable. The buildings do not bounce. The pavement does not wobble. The human brain achieves this stability through a complex system of internal subtraction. Every time the brain sends a command to the eye muscles to move, it also sends a copy of that command to the visual cortex. This copy is known as an efference copy, or a corollary discharge signal. It acts as an internal warning system. It tells the brain exactly how much the eye is about to move, and in what direction. The brain then uses this information to subtract the eye's movement from the incoming visual data. It is a biological image stabilizer, smoothing out the bumps and jitters of the organic camera. However, this subtraction system is not perfect. It relies heavily on context. To accurately calculate how much the eye has moved, the brain needs landmarks. It needs a frame of reference. In a normal environment, the human is surrounded by lines, corners, textures, and depth. There are door frames, table legs, horizons, and patterns of light and shadow. The brain uses these reference points to anchor its visual field. It compares the movement of the eye against the stationary background of the room. When a human stares at a blank wall, or a single light in a pitch-black room, this frame of reference vanishes. The visual landscape is stripped of its anchors. There are no edges, no gradients of light, no competing objects to provide scale or distance. The brain is presented with a sensory vacuum. This extreme state of visual uniformity is sometimes called a Ganzfeld, a German word meaning entire field. In this vacuum, the brain's stabilization system begins to fail. The eye continues its involuntary jitters, the micro-saccades, the drifts, the tremors. The eye muscles send their reports, and the brain attempts to subtract the movement. But without any external landmarks to confirm whether the eye moved or the object moved, the calculations become muddy. The brain receives the signal that the eye has drifted slightly to the right. Without a stationary background to prove otherwise, the brain makes a logical error. It assumes the eye remains still, and that the external point of light must have moved to the left. The autokinetic effect is the physical manifestation of this internal math error. It is the sound of the brain's visual computer running its calculations in an empty room, with no variables to work with. When we stare at a blank wall, our visual system is placed in a state of suspended animation. The human brain is a prediction engine. It does not merely record the world, it actively constructs a model of it. To do this efficiently, it ignores constant, unchanging inputs. If a sound is continuous, like the hum of a refrigerator, the brain eventually filters it out. If a smell is constant, the nose stops detecting it. The same is true for sight. A blank, featureless wall offers no new information. The brain, seeking to save energy, begins to power down its processing of the static field. Yet, the eye muscles refuse to coordinate with this shutdown. They continue their ancient, rhythmic dance. The brain, caught between a visual field that is fading due to lack of contrast and an eye that is constantly vibrating to prevent that very fading, becomes confused. It tries to match the physical tremors of the eye muscles with the lack of movement on the wall. The efference copy tells the visual cortex that a movement has occurred. The visual cortex, looking at the featureless wall, sees no change. In the absence of a clear background, the brain concludes that the point of focus must be sliding across space. This error is magnified by the brain's inherent bias toward motion. In the evolutionary past of the human species, detecting movement was a matter of survival. A rustle in the grass, a shadow sliding across a rock face, a distant speck moving along the horizon, these were the signals of predators or prey. A human who was highly sensitive to motion, even to the point of false alarms, was far more likely to survive than one who ignored subtle shifts in their environment. The human visual system is therefore hardwired to err on the side of motion. It would rather misinterpret a stationary point as moving than miss a moving threat that appeared stationary. Thus, the autokinetic effect is not a design flaw. It is a side effect of an incredibly sensitive, survival-oriented motion detection system. It is the price the human pays for having eyes that can spot a camouflaged predator in the dappled light of a forest. There is a strange, historical consequence to this visual quirk. For decades, before the advent of sophisticated radar and automated flight systems, night pilots were highly vulnerable to the autokinetic effect. A pilot flying through a cloudless, moonless night might find themselves staring at a single, distant star, or a lone light on the ground. To their eyes, stripped of the horizon, the light would begin to drift. Believing the light was an enemy aircraft or a lead plane changing course, the pilot would adjust their flight path to follow it. This often led to severe disorientation, and in many tragic cases, fatal crashes. The military had to train pilots specifically to combat this illusion, teaching them to never stare at a single light source for more than a few seconds, and to constantly sweep their eyes across the instrument panel to force a frame of reference back into their brains. Even in the safety of a modern apartment, the effect can feel unsettling. It is a reminder that what we perceive as reality is actually a highly processed, heavily edited reconstruction. The solid world is an illusion maintained by constant, frantic activity behind the scenes. But there is something deeply comforting about this failure of perception. The autokinetic effect occurs because the human brain is simply too active, too eager to find patterns, to ever truly rest. It is an engine of curiosity, designed to detect motion and meaning in the wild. When presented with nothing, it chooses to see something. It refuses to accept the blankness of the wall, and instead, invites the world to dance.